Well, there's going to be some times where top minus bottom is actually not going to help us out. And there will actually be some times when there will be an easier way to find areas like this area here. Okay? Now, notice we end up with three different functions. It's plus or minus root 3 minus x, and it's y equals x minus 1. What's the problem with trying to find the area using vertical rectangles? It's not really a problem. It's just something I'd have to figure out and do. We see the top minus the bottom, right? Top minus bottom is the line and the negative root 3 minus x. Top minus bottom, stay until we get here. What happens right here? The top and the bottom change. So if I were to use vertical rectangles, I would need two integrals. Where my first integral, and we're going to assume that these are at the whole numbers, and I think they are, is from -1 here to 2 here of the top minus the bottom, which is the x minus 1 minus the negative root 3 minus x. And then I'll have to add to that an integral starting at 2 and going to 3 of the new top minus the new bottom. I have to evaluate those. This can be simplified, but there's an easier way. Let me show you another example of a tough area to find using vertical rectangles. Flip to the bottom of, I believe, the next page, or the third page. One more. Yes. See that on the bottom of the next page? Okay? Okay. Now, write small because we're going to need some space, but discuss with your neighbors, how many integrals do you think you would need to find the area of this region right here? 4? Not quite 4. Not just 2. 3, but why? Look, where are we starting? We're starting from -2, okay? That's where the area starts. Do we have a top minus a bottom here? Yeah, we have the e to the x plus 2 as the top and the y equals 1 as the bottom. But then once I get here, what happens? The top is no longer e to the x plus 2. The top is now 2. The bottom is 1. Okay, and then I get here to this intersection, and all of a sudden the top and bottom change again. Now, we can find where these intersections are. It's not important, but I'm just going to list them off as like A and B. And I want us to write down the integrals. Actually, let's actually find the intersections. So this starts when e to the x plus 2 intersects with y equals 1. That's the log of 1, which ends up being 0. So this actually ends up being -2. So that's good. This intersection right here is when e to the x plus 2 intersects with 2. Take the log of both sides. I get the natural log of 2. And that's log 2 minus 2. Okay, so this x coordinate right here, log 2 minus 2. All right. The next one, we have 2 over x intersecting with y equals 2. That's right here. So that's x equals 1. So that's nice. And then the last intersection is when 2 over x intersects with y equals 1. And we get x is 1/2. No, x is 2. And so that's nice too. So we got one crazy intersection here. Okay, so let's write our integrals. The first integral from -2 to log 2 minus 2 is the top minus bottom. The top is the e to the x plus 2 minus the bottom is 1. Okay, good. Then you could consider this a rectangle's worth of area, but let's just use an integral to find it. It'd be log 2 minus 2 to 1 of top minus bottom, 2 minus 1. And then I have a third integral from 1 to 2 of the top minus bottom, 2 over x minus 1. Yikes, it's pretty intense, right? Well, let me introduce you to another approach to things. Go back. We have been using vertical rectangles, and we are comfortable with using vertical rectangles. A vertical rectangle has a height, which is a y-coordinate. The y-coordinate is given to us by equations with x's. So we plug in an x into that equation, like x squared minus 3x, and we get the y-coordinate. Does that make sense? And that's the height. The width is a very small change in x. In certain situations, not all situations, but in certain situations, like the two we just saw, instead of using vertical rectangles, we are going to use horizontal rectangles. Now, rectangles have a height and a width. What's skinny, the height or the width? In this situation, the height is skinny. What do you think we would list the height as if it's very, very small and it's a very, very small change in y, dy? Very nice. What is the width in this situation? It's an x distance, right? It's the distance from the y-axis to this x-coordinate, okay? Now, it's an x distance, but we are going to need this x in terms of y's. Now, if we were to write integrals, this would be an integral starting from an x value of 0 to an x value of 4. The height are my y's. However, my y is given to us by this function of x's, and my width is dx. So notice, vertical rectangles, x's. Watch how things change. Now look at this horizontal rectangle. We are actually going to sum them up starting at a y-coordinate, going to another y-coordinate. We're not going to go from 0 to 4. Instead, I'm going to go from a y-coordinate of 1 to a y-coordinate of 5. So all of a sudden, my integral changes to 1 to 5. My width times my height is different here. This is my height times my width. My width is an x distance, but my x distance will be given by this function of y's. The height is a very small change in y. Notice everything here, y's. Okay? So let's go back to my previous example. Actually, before I go to my previous example, we will use stuff that is similar to top minus bottom. With horizontal rectangles. What do you think I need to worry about? What would be the width of this rectangle right here? What is it, Mr. Schaefer? The right x distance minus the left x distance. It's the x from the right minus the x distance from the left. Well, The x distance from the right is h of y in this case. And the x distance from the left is k of y. So similar to top minus bottom, or integral using horizontal rectangles is going to be a right minus a left. dy, we are going from y's to a y. These equations will be x equals y's. Okay? Now we're going to do the previous examples that we've already looked at. Only we're going to do it using this alternate approach. So first thing I'm going to do is understand my horizontal rectangle and what it looks like. Now, we see we're between two curves. Do we see a right and a left? The right is the red sideways parabola. The left is the line. So far, so good? Does the right and the left change? No, they're consistent. The right minus the left will always be parabola minus line. Cool? Okay, great. Now, we're thinking about summing these up. Starting from a y-coordinate, going to a y-coordinate. So I can immediately say I'm only going to be using one integral, and my one integral is going to start from a y-coordinate of -2 to a y-coordinate of 1. The next thing I know is that the height of my rectangle is a very small change in y. Now, the only thing that's unique to this form that we're not used to is that we need x equals y equations in here. So an extra step that you will see that you will have to do for a lot of these is actually to solve these equations for x. So you have x distances in terms of y coordinates. And we want these right minus left x distances. That's the width of our rectangle. So this solve for x becomes y plus 1 equals x. This is my left distance. And here, I'm going to square both sides. Y squared equals 3 minus x. Add x, subtract, x is equal to 3 minus y squared. And this is my x distance to the right. Right minus left. Now watch. Quickly using my calculator, I'm going to type in both of those. Let's go back to the front. I had these two integrals. I had one integral from -1 to 2 of x minus 1 plus root 3 minus x. That was one integral. And then I'm adding an integral from 2 to 3 of, when I end up subtracting these, it's just this plus this, which is 2 of these. So just quickly, so that I can enter it in quickly, I'll simplify that. And I get an area of 4.5. I'm assuming it's 4.5 because my calculator is approximating. Let's look at the other way that I calculated this area using one integral. Now, here's a good question. How do I type in y's? Well, if I wanted to, I could type in y's, alpha y, and then dy, but there's no point, okay? It will produce the same as if I just replace these y's with x's. So just plugging things into our calculator doesn't care what we're doing. Sorry, it's a 3. 3 minus x squared, we can use x's minus, I'll throw in this. And what should we see? The exact same value. It's even more accurate because there's less craziness going on, okay? So isn't that cool? Now for this example, man, 2 integrals versus 1 integral, no big deal. But let's go back to that other one where we had to use 3 integrals. We'll go back here. I had to use 3 integrals, and I had to find an intersection that was at log 2 minus 2 to be able to write the correct integrals. Flip-flop things. What if I use a horizontal rectangle? Discuss with your neighbors. How many do I need? What would be the boundaries? And what do you have to do to set up your integral? Like, what's the only step that is actually a little bit involved? Now, what's very, very important, everybody, is to draw this horizontal rectangle and understand it. You have to understand that it's got a very skinny height. That's dy. If I'm summing up all of these areas of these rectangles, I'm starting at a y, going to a y. So I'm immediately saying I'm starting at 1 and I'm going to 2. The right minus the left does not change, so I just need one integral from 1 to 2. What's the one thing I'd have to do, though? Solve them for x, because this width is a right x minus a left x. The x distances can be given us if I plug y into some equation where it's x equals y. So the only thing I have to worry about is I have to take this and solve it for x. X equals 2 over y. This, a little bit more involved, but I know that's the right. 2 over y is the right. This, y equals e to the x plus 2. I'll take the natural log of both sides. I'll subtract 2. And I get log y minus 2 equals x. Make sure that's in parentheses. And if we have time, and I don't have time, because man, even doing this is going to take us a long time to plug into our calculator, I would see that this sum of these 3 integrals would be the exact same as this one integral. Okay? Now, depending on the situation, we will either have to use horizontal rectangles or it's more advantageous for us to use horizontal rectangles. I'd like us to practice being able to go in both directions. So let's find an area using both horizontal rectangles and vertical rectangles. I have y equals x, y equals 2 minus x, y equals 0. Here is my region. I will tell you right now that they intersect at 1, 1. And 2 minus x will intersect with y equals 0 at 2, 0. Okay, step 1, vertical rectangles. How many integrals do you need? Write those integrals. This is why it's important for either direction to be able to visualize the summing of rectangles. You guys are still probably, most of you, stuck in the global mode, where it's just like, I'm finding the area from 0 to 2. If you stay stuck in the global mode and you think that you can find the area with one integral using dx, you're wrong. Why? Because the top is y equals x from 0 to 1. At 1, the top changes to 2 minus x. So this is not correct. what helps me do that is visualizing a vertical rectangle. Use your pencil, use something where you have some sort of line and think about, okay, I'm starting from here. I have the y equals x until there, and then I switch to the 2 minus x. So we need two integrals using vertical rectangles, one from 0 to 1 of the x, and then another one from 1 to 2 of the 2 minus x. You can have a minus 0 at the bottom, but minus 0 obviously doesn't do anything. So this is our vertical. This is what we're used to. Now, flip-flop things. Put it on its side. And give me the equivalent using horizontal rectangles. Right minus left. Okay, so if I'm thinking of horizontal rectangles, use your pen, okay? Flip it on its side. Start at y's of 0, go to y's of 1, right? Do we see that? We're going from a y of 0 to a y of 1. We're going to use a right minus left, but it's an x from the right minus an x from the left. The x will be in terms of y's. The x will be in terms of y's. So this is x equals y. So that's same as y equals x. And this would be 2 minus y. So right minus left. You put both of those sets into your calculator, you get the same answer. Do it by hand. It's actually something we can use geometry to find. Okay? Questions? What is important about this? Actually visualizing the rectangles and their summation. Not thinking globally, thinking locally. Okay, I'm going to skip this one, go to this one. Again, we're going to find this area using horizontal and vertical rectangles. Go ahead and do that. You can then plug it into your calculator to make sure you get the same values for both. Oops. There we go. Type both of those integrals into your calculator. Zero to 9 is 6 minus 2 root x, and 0 to 6 of y squared over 4, or y over 2 squared. We get 18 for both of them. Does anybody have any questions, have any issues with either of these approaches? Some keys to remember. X's, dx, x's, x's. Y's, dy, y, y. Your variables end up having to agree with each other so that we have what we need. Another key is to draw the rectangle or use your pencil, some sort of device where you can see, okay, I'm starting from here, that's x equals 0. I'm going to here, that's x equals 9. Then flip them, use a pencil or something, start here at 0, go to this y coordinate of 6, right minus left, in this case the left is 0, the right is the x coordinate, which is a function of y. I plug in a y coordinate into an x equals y equation to get the x distance. Okay? Now there are some times when you will be given equations like this in x equals y form. And what students aren't good at is graphing x equals y equations. Okay? But it's not hard so long as we just keep things in order. Now, we don't have y coordinates. If you talked about this one here, it's giving you y equals -1 and y equals 1. Those are going to be your boundaries. And just to show you, and we could go back to this example, x equals -y squared plus 2, how to graph it, just throw in y's and you'll get x's. So like I'll throw in y equals -1. That will be -1 squared, take the opposite of it, add 2, so that would be 1. That would be the x coordinate, so that means I have the point 1, -1. So 1 is the x coordinate, -1 is the y coordinate. I look at 0. I'd get 0 squared plus 2. That would be 2. 2 would be your x coordinate. So then you have to flip-flop them and say, okay, I have the point 2, 0. See how that works? You can do the same thing for 1, and you'd get 1, 1. Ends up not being a function, but that's okay. This would be the region. What you'll find is that you didn't even need the sketch. You just needed from -1 to 1 of the -y squared plus 2. There's no right or left. There's just the one function. Okay? Now for this guy here, similar to with quadratics and lines, we need to find the intersections. So you'll set the equations equal to each other. These are not equations that we can easily solve. Some of them are easily solvable for y and then graphing it that way. But I'm going to do it a different way. Okay? I'm going to first find the intersections, just like I would. Solve this quadratic. Factor. And what I'm getting are y coordinates where these graphs intersect, when y is 2 and when y is -3. I can plug in 2 and -3. I see when y is 2, x is 0. So I get the point 0, 2. When y is -3, x is -5. So I have the point -5, -3. Now, it's especially important here because you don't know what this looks like. We do know that this is a line, so I'm going to connect that knowing that that's a line. It's just a y equals x plus 2. Okay, so there's y equals x plus 2. For this one, I don't know if I'm to the right or to the left. I want green. Let's go green. We'll stay with red. What we will do is plug in some points in between -3 and 2. So let's do that. If I have y is 0 of x equals 4 minus 0, so x is 4, I have the point 4, 0. So 1, 2, 3, 4, 0. You can say when y is 1. When y is 1, x is 4 minus 1, so that's 3. So I have the point 3, 1. So 3, 1. If I did -1, it would also be here. And we would see that we end up with this sideways parabola. Now, after kind of understanding that sketch, and it's important to be able to do this x equals y sketch. You'll see a question like it. You'll be able to set up your integral. You're starting from -3. You're going to 2. Your right is the 4 minus the y squared. Your left is the y minus 2. Okay. Now, I can ask you the same type of question from the last lesson about finding a line that splits an area into 2 equal parts. Only the line is now a y equals k. I'm just going to set up the integral for this one, and we're going to do it for the last one. Okay? In this situation, we'd go from the bottom to k, the integral from -3 to k of the right minus the left would have to be equal to half the total area from the previous one if we use our calculator. Okay, I'm not going to show you this, but that's the setup, okay? The line is now horizontal, so I have to use horizontal rectangles when I'm summing them up. Okay? Let's go to this one. This is an actual AP free response problem from the past year. And we got a part A and a part C. We got 2 equations, log x and 5 minus x. They intersect at a point that we need to find. It's not easily found. Nope. So I have to use my calculator. We got log x and log x and I'm going to get it. Log x and 5 minus x. Okay. New standard. And there's the region here. This intersection, they don't tell us what it is. We have to find it. The intersection is at .6934414 and 1.3065586. We need that. .3065586. 1.3065586. Oops. Okay, good. Let's find the area R. Go ahead, find the area R. Do whichever way you want to do it. You don't have to use horizontal rectangles. You can use vertical rectangles. Let's find it. For a challenge, do it in both ways, because you can actually find it in both ways. Make sure you solve for x equals y. Okay, I got them both. Here we go. I have my vertical rectangles. I'm starting them. Whoops. Sorry. Jeez. See, it's like I didn't do it. And now that I'm actually using a pencil, using a line, I realized, nope, we're not starting at 0. Screwed up. We're starting at 1. This is the process you have to do. Start with your pencil. Where do I start? I don't start at 0. Start at 1. Where do I go to? I go to this x-coordinate of 3.69344414, and I'm using the y equals log x as the height. Then I switch. Starting at 3.69344414, going to 5, I'm using the 5 minus x as the height. I can't just do it in one integral from 0 to 5. It won't work. Okay? Do we understand that? Why I need multiple integrals? Now, if I flip it, using horizontal rectangles, all of a sudden, yes, I am starting at 0. And I'm going to this y-coordinate, and my right and my left are consistent. So I only need one integral, 1 from 0 to 1.3065586 of the right minus the left. Now remember, the width of this is an x distance. The x distance is in terms of y's. You need your equations in y's. That's the width. The height is a very, very small change in y. Okay? Now, if you were not comfortable doing horizontal rectangles, you are not going to be able to get part C. Part C says the horizontal line y equals k, or some line y equals k, divides the region R into two regions of equal area. Right, but do not solve an equation involving one or more integrals whose solution gives the value of k. Let's try this. We have a horizontal line that splits this into two equal regions. Set up an equation involving an integral, so you don't have to actually find k, that you can use to find the value of k. What do we get was the area, actually? 2.96? 986? Beautiful. Awesome. Awesome. Because this is why you have to think about, here's my rectangle, okay? Where's 5 minus x? It's over here. Is 5 minus x going to have anything to do with this rectangle right here? No. So this is why you got to use your pen. You got to kind of think about my rectangles. There is no bottom. The bottom is y equals 0. So it's just the top of the log function until I get here. Once I get here, all of a sudden my rectangles are using this graph. Okay? That's how we have to have things thought of. Excellent. Okay? The key for this is that my area starting at 0 going to k of my right minus the left, that will equal 1/2 whatever my area I found from part A was. We should be able to find this actually. We would have the antiderivative from 0 to k. I'd have 5k minus 1/2 k squared minus e to the k minus, if I plug 0 in, I'll have 0 minus 0 minus 1, and that will equal this. I can plug this into my calculator, and I can find the intersection. It's important when you plug 0 in, you don't get 0. Okay? Thank you, guys. Really